Okay, so I'd like to start by thanking the organizers, in particular Rukmini, for inviting me to this meeting. And I chose to talk about this paper that I finished recently with Roger Bilavsky and Markus Röser, which connects rather closely with the title of this meeting, which has integrability already in the title, as you see. Okay, so so this is the plan for my talk. So it's about a system of differential equations that is very similar to the Nahm equations that people are familiar with from the physics of monopoles, but it's not quite the same. So I'm going to explain you more, why they are different, why they are similar, and I'll maybe start with so by the way, the main reference is this paper. So this is the archive number. You can retrieve it from the archive, but it's also already in the pipeline for the Quarterly Journal of Mathematics. So it's going to appear soon there. Okay, so I'm going to start with actually some motivation. So this is a well-known story. Charge rank duality. Maybe I should be more precise and write here Riemannian. Charge rank duality. So this is this story when you start with the anti-self-dual equations in R4. Okay, for example, for group SU2. Okay, so the anti-self-duality equations, everyone is familiar with them. Okay, and then there are dimensional reductions which are important, and they have been a source of great attention from physicists. So there's the Bogomolny equations to 3 dimensions. Okay, so there's for the Bogomolny equations there's a Higgs field, and then you can get that by as a component of the gauge field, and then you make the so the fields invariant in one direction. Okay, so this is the Bogomolny equation in R3. Okay, then you can also reduce to 2 dimensions. You get the Hitchin equations. This is a separate story, so to say. And then in 1 dimension, you have the Nahm equations. Okay, so maybe I'll write it like that. Okay, and and this is actually so studying this system of ODEs that you get by saying that the fields are going to be independent in 3. So in translations in 3 directions, you have actually a tool to construct solutions to the Bogomolny equations and monopoles. So there's a recent story where people actually have done this very explicitly. So this recent work, by so some people, in Edinburgh. Okay, so so there is this thing called the Nahm transform that relates these 2 systems of equations, and then it swaps the charge of the monopole. So there's a topological charge associated to in this situation, which is going to be the rank of the matrices that appear in this ODE. Okay, so this is, for example, for UK, so K by K matrices, anti-Hermitian, and here there's also reduction to 0 dimensions, which is this ADHM transform. Okay, so 4 dimensions relate to 1 dimensions. 2 dimensions are sort of self-dual, and there is this this relation between 3 dimensions and 1 dimension. Okay, so the question is, so what happens if you replace R4 by So flat space, but with split signature. So you have here plus, plus, minus, minus. So this is the main question that maybe you can ask when you're wondering why. So why are these Nahm-Schmid equations? Why are they interesting? And then what people know is that, well, if you reduce, so for the metric in R22, so if you reduce to 3 dimensions, you have an equation which is similar to the Rukmini equation for monopoles, but for the metric of R1, so R12, okay, and these are called the Ward, so the Ward equations, okay, and and there are, so they are integrable. The question, so you might wonder, so is there then a way to look at a sort of complementary dimensional reduction and have an ODE that you can use to study solutions of this equation, okay? And this is really what the Nahm equations, so the Nahm-Schmid equations are, okay? So let's just, okay, so so there is then a whole story that is so very well known that, for example, these equations develop poles, and then the residues of these poles they are representations of SU2 and so on and so forth. There are moduli spaces that coincide on both sides. So this Nahm transform is an isometry for a metric which is hyperkähler on these moduli spaces. And then there's this aspect of integrability where you can actually solve explicitly. And there's also, maybe even better, there is a geometric way of looking at this integrability in terms of spectral curves and so on. So this is what I'm also going to explain. Okay, so now the Nahm-Schmid equations. Okay, so you start with the anti-self-duality equations in this metric. Okay. And okay, so you fix a compact Lie group with Lie algebra G, German G. Okay. So I have so with add invariant in a product. Okay. And then you have the anti-self-duality equations. So in the signature, okay. So this delta is a connection, so a G connection. Okay, so in a trivialization, you write it as so D minus, so D plus Ti dxi. Okay, and oops, is this still working? Right. So these deltas with the these are so I evaluate with the the basis of so vector fields, and so now I say that the fields are going to be independent in the one so assuming invariance in the 1, 2, and 3 directions, then you get that, you get a system of differential equations just for one variable x naught. I'm going to denote as t. Okay, so so I can say that these delta naught becomes that, and then the other ones are just ti. Okay? So this is what you get. You get the system, so ti, so t1. Okay? So these are matrices, if you like. If you have So these are the Nahm-Schmid equations. Okay? So the Nahm equations have the following difference. Just this minus sign is different. So this minus sign is a plus in the Nahm equations. But this is going to make a whole difference, as you will see. Okay? Anyway, so there is. So you can think of these as, a system of equations on the line, and there are gauge transformations acting. Okay, so gauge transformations are just maps to the group. Okay, and then so the point is that I can take a solution. So I'm going to use this t to denote this quadruple. Okay, so so this is going to be transformed to and then just conjugation for the other ones. Okay, so these transformations preserve solutions. Okay, and so this means that we can also use this freedom to set t naught to 0. So can use a solution u of u t naught to set not to 0, okay, and then you have, the equations where you have, the reduced form of the equations where you get rid of these brackets here, okay, and and you get to basically the version of the equations that are more related to these, except that one of the equations has a minus sign. Okay. Anyway, so. Okay, so here is one way in which these equations are different from Nahm's equations, the familiar Nahm's equations. So proposition. Okay, so this ODE preserves the gauge invariant quantities so Ti, okay, so T1 mod squared. So these Ti's that represent the connection, they are valid in the algebra. So I'm using these inner products there, and so these are conserved quantities, and also inner product of Ti and Tj for I different from j. So these are conserved. This is just a calculation, just using the equations, taking the flow under these ODEs, and you can see that these are going to be invariant. Okay, so just compute. So corollary Okay, so solutions of Nahm-Schmid are so regular for all T in R. Okay, so they are globally, they exist globally. So this is in contrast with what we know about the Nahm equations, where there are these poles, and so this is already yeah. So this is just easy to prove. So you just take yeah. So for each I, you take yeah. So let's say we work with the reduced form of the equations, and then you look at these yeah, at this quantity. So which yeah. So it's going to be finite if the solutions are regular, and this is bounded above by this quantity here, obviously. Okay. Right, and we see that this is just yeah, the sum of so conserved quantities. Okay, so this is conserved. So if you start with the regular solution, then the flow will preserve regularity. Okay. So any questions so far? So this is all very simple. It's just introducing these equations. So moduli spaces. So we want to define space that characterize solutions modulo these gauge transformations, just as we do for the Nahm equations. Okay. So I'm going to consider a domain which is compact. Okay. So over a compact interval. So I'm going to denote by U. So for example, 0, 1. Okay. So I look at the space of fields, which are yeah, if you like, these matrices valued in the Lie algebra. Okay, so so they are tors from U to. So I can just write it like this. So G, so the Lie algebra, yeah, so tensed with R4. Okay, such that so I'm going to say that I'm going to impose that they are of class C1. Okay, so this is the same as obviously C1, so C1 functions from U to the Lie algebra, yeah, with 4 components. Okay, so now have some facts. So these are sort of not so just easy theorems that we have in our paper. So or just observations. Okay, so the first fact is that the Nahm-Schmid solutions form a Banach. So the set of solutions form a Banach submanifold of a U. Okay, so here I'm using, for example, so with the C1 norm. Okay, so it's a rather well-behaved infinite-dimensional manifold, if you like. Okay, so this admits, so this set of solutions admits an action by so smooth action by the Banach Lie group of gauge transformations, so GU. Anyway, so yeah, because I have to differentiate, yeah, when I do gauge transformation, I have to differentiate this U. So here I'm going to impose C2 regularity. Okay, so this has the Lie algebra, also C2 functions valued in, the transformations are valued in G. the Lie algebra are C2 functions from U to the Lie algebra, okay? And this has a normal subgroup. So there is a normal subgroup G naught naught where I fix the values at the extreme of the interval to be just the identity. Okay, so I take. Okay, so. So this is the identity. Okay, so there is so this acts. So okay, so this acts freely and properly on A. Okay, and now we can define the moduli space as elements in A solving the Nahm-Schmid equations, okay, and divided by this group, this G naught naught, okay. Okay, so the result, which is already maybe not too obvious now, is just a very concrete description of this quotient. So there is this theorem. So M is going to be diffeomorphic to G times G times G times G. Okay, so the way you prove this, you have to find a slice for this action, and then you identify the elements of the slice with this. So elements of these products. Okay, so symmetries. Okay, so we know that we have this bigger group acting on solutions, preserving solutions. But we are quotienting by the smaller subgroup, so there is an action of G of the quotient. So this is two copies of G. So this acts on M. Okay, and then maybe less obviously, there's an action of SO12. Okay, so if you have a matrix in this three-dimensional Lorentz group, you have you can take you can transform like that, and these still preserve solutions. And moreover, these two actions commute. Okay, so there's actually symmetry by G cross the Lorentz group. So this Lorentz, so the fact that you have here this symmetry, is already saying that maybe it's not too far out to expect that these equations have actually something to do with these word solitons. So everything clear so far? Yes. This is diffeomorphism. Yes, I mean this is what I said. So you yes, well, yeah. So you have to first, you need to, So this factor here is basically has to do with the gauge transformation that straightens out this U naught, and then basically this is has to do with the the other matrices. So this is So there's one direction which is sort of special, as we know, and this is why you get like a product where one of the factors is not just equal to the others. Sorry, J, which T, no, this is T, yes, okay, sorry, yeah. There's going to be more structure. I mean, so these moduli spaces, the next section is going to be about geometry of these moduli spaces. So yeah. Yes, yeah. So that's I think that's actually a good question because yeah. So in the yeah, there is some SO3s around as well, but yeah, but here this is the isometry is S12. Yes. So there is this is it's like rotating these sort of spatial parts of the these 1 to 3, and the minus sign means that you cannot go to SO3. But there is an interplay between, the hyperboloid in the Lorentz space and spheres and so on, and this is going to be. I won't actually have time to explain that completely, but I'm going to show you some things about that. Okay, so can I just erase these now? Okay, so now just like the case of the Nahm equations and magnetic monopoles, we know that there is this nice metric hyperkähler on the moduli space, and then there's also this twistor space, and so the moduli space is a complex manifold in a different. So there's an S2 of different ways of putting complex structures there. So there's a similar story here, but now the relevant geometry won't be quite. Hyperkähler geometry. It's going to be some kind of variation of hyperkähler geometry, which is called hypersymplectic geometry. So this is this second keyword in my title. Okay, so now I'm going to give you some, so just flash you some, so basic facts about hypersymplectic geometry, which maybe you're not familiar with because this is maybe not a very standard topic. So definition, so a hypersymplectic manifold is a quintuple, so a manifold, so it has to have dimension a multiple of 4. So it has a metric, and then also endomorphisms of the tangent bundle, okay? So, but now so G now is not required to be Riemannian. Okay, so where G is so a pseudo-Riemannian metric of signature 2K, 2K, so split signature again. Yeah. IST, so endomorphisms of tangent bundle, such that the okay, so they are parallel, okay, and skew adjoint. They satisfy the algebra of. So now it's not the quaternions, it's the split quaternions, okay? So you have again I squaring to minus the identity, okay? But the other two, so this is it's going to be, a normal complex structure, but the other ones are not. They square to the identity, not minus the identity. And then you have also, so IS is T and so on. Okay, so so this is an almost complex structure that you're familiar with. This is called usually a local product structure, and the reason is that so S, or T is called so it's called local product structure. So the reason is that so locally you can split the tangent space into the eigenspaces of plus and minus 1, right? at every point in a canonical way. So in fact, you have, so there's a way of understanding the manifold as a product like that, but in a canonical way. Okay? It's a local picture, yes. Yeah. Okay. And now, just like in this more familiar situation of hyperkähler geometry, you have these symplectic forms that you cook up with the metric and the endomorphisms. So you have the omega I, omega S, and so on. Okay. So yeah, so they are. So there's a similar story. So they are closed if and only if these are integrable and parallel, and So you have. So these forms are also useful. And then there is yes, and then you also have that maybe just an aside that the holonomy is in S. So this is yeah. Three forms, yeah, okay. Yeah, it's if and only if. What I said is if and only if, yes. Yes. Okay, so the holonomy is in, so SP to KR. In particular, you can see that these metrics have to be Ricci flat. Okay, and now there's also a notion of a quotient, but that is actually a bit different from the hypersymplectic quotient that people are maybe familiar with. So this is the situation. So you have a group acting on the hypersymplectic manifold, okay, and this action is Hamiltonian for all these so symplectic structures for all these omega IST. Okay, so you can define a moment map which is three valued, so three components. Okay, and then you have the following situation. This is so then if zero, so the zero here is a regular value. Okay. And okay, so this condition is not in the so you don't have to include it in the hyperkähler. Yep. Equivalent. Yes, I think so. Yes. Well, so in the same sense as in hyperkähler geometry, yeah. Yes, I am not sure about that. Yeah, so okay, we can maybe discuss this later. Yeah, right. But well, I mean, I guess the usual representation, right, in Minkowski. Yeah. So if zero is a regular value, and so these the zero set, so so the metric is non-degenerate, so you have to impose this extra condition. Is so in G is non-degenerate. So well, it is non-degenerate for G. Okay, so the metric is non-degenerate on the zero set on the cut locus, then you can form the quotient, and this has this carries the hypersymplectic structure. Then this carries an induced hypersymplectic structure. Okay, but in many cases this is not. So it is not global. You have actually that there is really a degenerate locus, and then you cannot extend the hypersymplectic structure everywhere. So this is also what makes this Nahm-Schmid business a bit more difficult than the Nahm sort of industry, if you like. Okay, so maybe I'll write explicit. So often. So the non-degeneracy, occurs only in the complement of certain degeneracy locus D. Okay. Right. So this is the end of my digression on hypersymplectic geometry. Okay. So So now, as you might already expect, so these moduli spaces are going to have this kind of structure, and just like in the Nahm business, what is this quotient construction? If we can get a quotient construction, then yes, this is useful to understand in more detail what these geometric ingredients for the hypersymplectic structure. Okay, so let's just do that. So let's start with the space of fields first. So the tangent space to A at one of these Lie algebra valued functions is okay. So C1 UG tensor R4, but now I'm going to say that these R4, I'm going to identify it with R22. Okay, so this has an L2 metric. Okay, so I'm telling you basically where this hypersymplectic structure comes from. Right, so this has a natural L2 metric, and this has this metric in split signature. So you take the product, the tensor product matrix. So so in Dow, so A with the product metric, which is flat, yes, and then there's also an action of the split quaternions here. So this algebra of split quaternions that I'm calling B, so the split quaternions. They act here. I mean, so there's, I'm not going to write down explicitly but there is a way of, cooking up. So this is a representation, if you like, of these, split quaternions. And, okay, so theorem. So this is basically saying where this geometry is coming from, and that you can sort of push it through to the modular space. Okay, so you send it to the modular space. So G naught naught. So this action on A, so preserves this flat, hypersymplectic structure. Okay, and is three Hamiltonian. So Hamiltonian with respect to the three forms. Okay, so there is an identification of the modular space with okay. So the point is that when you when you compute these moment maps, you're going to get basically the Nahm-Schmid equations. Okay. Okay. So the generosity locus D, okay, is invariant under the symmetries. And well, I think you should say, so here you should say, yeah, so not in the moduli space, but here, so it's maybe G, yeah, G, so invariant. And yeah, so and then the, yes, so the hypersymplectic structure descends, okay, to open set in, yeah, the, so cut locus minus this D. Okay. So now so these are sort of things that we explain in detail in this paper. And so you might think, so is there really the generosity locus? And yes, so one thing that you can say is that if the Lie algebra, well, or the group, so is non-abelian, then there is a non-empty, the generosity locus. So you have to really deal with this. Okay, and in the paper we also give some criteria to identify so the points of the generosity locus. So it's a bit technical. I'm not going to explain this now. And yeah, and maybe what is worth writing down is that there is some kind of description, at least local description, of the geometric structures. In terms of these, yeah. Okay, so maybe geometric structures. So can be identified locally as follows. So yeah, so locally, so it's like so in a neighborhood of points where the well, so basically it's when T, this is what we can do, where the T0 and so T2 and T3 are small. Okay, so and away from the generosity locus. Okay, so this is what we get. So as a complex, okay, so as a complex symplectic manifold, so M naught I. Okay, so this is the complexified. So this is basically the zero section of the cotangent bundle of the complexification of G. Okay. Okay, so this has a canonical symplectic structure, and this is basically. You know, there's a complex symplectic morphism, and you can identify, you know, for T. Yeah, M0. Yeah, M0 is the yes. Sorry, yeah. So M0 is that. Yes. Sorry. So it's a subset because I am taking out the generosity locus. So it's an open set of the moduli space. Yeah, open set, yes, okay. Thank you. Yeah, and then as, so this is like for the complex structure, this is really what you have. And now for the local product structures, so maybe I'll write, so as, this is how it's called, so as a parakeller manifold. So parakeller means that it's a keller, but with the endomorphism that squares to the identity, not the minus identity. As a parakeller manifold, yeah, this thing. So so here, this twiddle means that it's not a global picture. It's just close to this, you know, this yeah, so small t not in T2. So yeah, it's just the same as scalar, but you replace the complex structure by the omega. Yeah, yeah. So this is the diagonal in the also of canonical structures. Okay. Okay, so so this is basically there are a lot more details in the paper, but yeah. Well, I mean, you can see that the dimensions are right and so on, but yes, but this is actually it's a local picture, so it's not a complete. Yeah, I agree that this is not maybe very satisfactory, but we can only have this. Yeah, we only have this picture locally. Yeah. Okay, so and now I have to because this is a meeting on integrability, I have to tell you about that. Okay, so integrability. Okay, so yeah, it's what I wrote there. So Lax pairs and so on. Yeah, and so forth. So this is yeah. So it's a picture which is similar to the Nahm case, and this actually ties up well also with a version of twistor theory, which is relevant for the Nahm-Schmid equations, or even for maybe more generally hypersymplectic manifolds. But yeah, it's a bit more involved. So the twistor theory is a bit more involved, and there are things that that are very nice in the hyperkähler case, which don't quite extend, unfortunately. But then, yeah, so you have here a spectral parameter. Okay, if you like a coordinate in P1, okay, and the point is that now you can also recast the Nahm-Schmid equations, as a Lax pair. Okay, so so maybe I'll write this. So this is actually a convenient notation. So T naught in T1 So I did not write the moment maps and so on. So maybe this is actually going to be more transparent for people that are more familiar with the hypersymplectic moment maps, hyperkähler moment maps and so on. So if you define these matrices like these, so there is this is how you can rewrite the Nahm-Schmid equations, and this actually is nice because it makes clear that there's also a complex equation and a real equation, just like you are familiar with for when you do these quotients and so on. Yeah. So these are the Nahm-Schmid equations. And now, now if you look at these combinations, beta minus that, and T plus, this is just definition. Okay, so easy check that the Nahm-Schmid equations are equivalent to so. Okay, this Lax pair. Okay, and now you have all these all this machinery which is familiar that you can you have you have spectral curves and so on. So there is a, so this flow preserves the, So spectral and then so now I'm going to assume that you have dealing with this case. Okay, so there's a spectral curve. There's a spectral curve conserved by the flow. Okay, so these conserved quantities that I had at the beginning that were useful to show that there is this regularity property, this global regularity, they appear as coefficients of this spectral curve. So the nicest way to So you can think of these again geometrically in terms of so line bundles of P1 and TP1 and so on. And okay, so the spectral curve, you define it like this. So it's okay. So you have here a coordinate zeta. You have a coordinate eta. So coordinates eta zeta for the tangent bundle, okay, and again, just like in the Nahm situation, the spectral curve is going to be a curve on this surface, which is the tangent bundle of so the total space of the tangent bundle to P1. Okay, so you have eta zeta, okay, in so TP1. So TP1 is, a line bundle O2, So TP1 such that, the determinant eta minus T. Okay? Okay, so genus n minus 1 squared. So this is very similar to the Nahm situation. Okay? But now, one thing which is very different is that so there's going to be also a reality structure, okay, and so there is so invariant reality. Okay, so here, so if you remember in the Nahm situation, the relevant reality structure was anti-holomorphic involution for TP1 that lifted the antipodal map. Okay? And the antipodal map has no fixed points. And here you have something different. It's a lift of that thing, which now has fixed points. Okay? So there's going to be a circle which is going to be fixed by reality, and this circle plays some role. So there's this P1 you can see as also like complex structures that you can put in the hypersymplectic manifold, and then this circle of complex structures that are fixed under reality. They play a special role in the twistor picture, in the twistor theory. So there's going to be some kind of something which is not going to be very nice over those symplectic, those complex structures. So I'm not going to explain this, but sorry. Yes, just from that, given a solution, you have a spectral curve by this formula, and then you observe that, yes. Thank you. Sorry? Oh yeah, no, I was just linking to this first part of my talk where when I said that for the Nahm-Schmid flow, there is this property of global regularity, which is not a feature of Nam's equations, right? These particular conserved quantities that are used to show these, right? So they appear here as coefficients of the spectral curve. Yeah, so just that. Okay. So now you have also this picture of linearization. Okay, so I still have 5 minutes. Okay, so so the linearization means that I can see the flow as a linear, so linear flow on the Jacobian, right? So this is maybe how you look at. So there's F. So you look at this sheaf, which is the co-kernel of eta minus t zeta. Right. So this is a semi-simple sheaf on sigma. Okay, with this property. Okay, and now you can look at so geometrically you can look at the flow as this bundle. So there's well in general there's a sheaf, but it's going to be a line bundle in some sort of situations that are natural. So you have this L is a fixed line bundle. So it's a bundle over TP1. Okay, so this is sigma sits there. You can pull it back to sigma, and this is a bundle with transition function. So in the usual sort of patches that you can see that sigma. So the zeta is got by stereographic projection, then eta is induced, and so on. Okay, sorry. Okay, so so maybe I'll go back to here. Yeah. Okay, so again, so it's so there's this F there, and then this co-kernel sheaf, and then so I'm saying that the flow is just if you like the flow of this bundle here, where L is a bundle over TP1, okay, and then you can pull it back to sigma, okay, and L has a transition function. So exponential of eta over zeta. Right. So this is a real. So it's invariant under this reality structure that is acting here. Yeah. Well, actually acting here, but so this is real in this sense, invariant by the. Okay. So this is just very similar picture of the Nahm situation, but now it's a bit. So the properties of these bundles. I mean, it's a bit. There's a special. So the properties that satisfy are a bit different, but I'm not going into that. I think I'm going to finish by giving you some example of explicit solutions. Okay, so when you have integrability, this is what people expect. You can solve things explicitly, and Okay, so explicit example. So this is when the case where G is SU2. So this is the simplest case that would correspond to the Nahm equations for two monopoles. Okay, this is the situation which is most studied. Well, I mean, you basically for monopoles you can do everything. Okay, so you have you have even an explicit description of the metric, on this moduli space, this Atiyah-Hitchin manifold and so on. And okay, so I'm going to work with these equations which are so in the reduced form. So T0 is 0. I make an ansatz, Ti, Fi, Ei. So Ei is a standard basis of the Lie algebra, just 1 over 2i times the Pauli matrices. Okay? So these Fi are functions. Okay? So I substitute in the Nahm-Schmid equations, and you can show that, yes, there is, so you can solve these equations, and you get elliptic integrals again. Okay, but this, so I'm going to okay, so it's, there's an explicit solution, so all the solutions are of this form. So this was written down in a thesis, Oxford PhD thesis by Matsoukas. But we also, we include this in the paper with reference to the thesis. Okay, so these are Jacobi elliptic functions, and A, B, and kappa are constants. Okay, so this is the general solution. Okay. So this is periodic. So this is how you get, so it's a periodic solution. So when kappa is in, so not 1, so this is periodic. So period, so for this period, this is a period. So that's why you get this global regularity. So they are these solutions are periodic, and then you can write down the spectral curve too. So yeah. Just like for 2 monopoles, you can write all the spectral curves for 2 monopoles. So eta squared equals okay. Right. So I think I'm already over time. So I did not tell you anything about this twister picture, which is a little bit involved. Let me just tell you that the way we do it is that we go through some very general construction of twistor spaces by Bailey and Eastwood, and then we impose the relevant reality conditions. So it's the strategy. You can also do that for hyperkähler. The hyperkähler twistor spaces, but the story is a bit more complicated in this case. So I think I'll stop here. It's just a bit more complicated, as it has these extra features that you have. So the twistor space is not completely determined by the hypersymplectic manifold and so on. Yeah. Yes. So there's So the situation. So maybe this is So in the twistor picture, you have you have the twistor space also mapping to P1, right? And there is this special S1 where which are the fixed points for the reality structure, right? And then there is, so the complement of this circle is actually, you can think about it in terms of Lorentzian geometry. And it's actually more natural to see it as, as a double-sheeted hyperboloid, in R1, R12, okay? And yes, and then there is an action. There's an action on of SO12 there, which preserves this. Yeah. So this is this two-sheeted hyperboloid is the part. So it's a set of complex structures for which this twistor space is almost what you expect from the hyperkähler situation. But there's this other complication that, yes. To be honest, I didn't look at that, but I suspect it's again Hitchin's equations. I guess. I mean, it's going to be. Yes, I have not actually. Yeah, there's going to be. I think this equation that says that the Higgs field is homomorphic is going to be the same. It's homogeneous, and the other one. I'm not quite sure. I'm not sure if you get something different, but I didn't check really. Yeah, I haven't checked that. We can do this calculation now, if you like. I think this is almost the same as asking, when you have the Nahm-Schmid equation, you have two minus signs or something like that. Yeah. But then it's the same. It's just a rescaling over a minus sign, and you don't have anything different. So this situation is different from the Riemannian case, but I think this is basically the two situations that are qualitatively different.